Hello and welcome, and this is Mr. Dolph, and today we're going to have a 10-minute video lesson as an extension discussion of our topic about field. Now, field is just a region in space where an object experiences a force at a distance. And the reason being is because there are charges that exhibits an electrical field. So, Coulomb's law would like to quantify this magnitude of force that an object may potentially experience. And to start with, let me just draw two identical charges positive. When we have two identical charges such as positive charge, they all exhibit a electric field. And once one charge is under the influence of each other's electric field, they will experience a force of repulsion. They will push each other away because they don't like each other. By the way, this is in a vacuum. On the other hand, if we have one positive and the other one is negative, they will still exhibit a electric field. And once they are under the influence of each other's field, they will experience a force of attraction. So there is a force involved here. The only difference here is that when their charges are similar, they will repel, and when they are opposite, they will attract. However, if we're going to place these two charges in a different environment, such as a rubber, right? So if we're going to put this positive with another positive in the rubber, they will still exhibit a electric field. The same thing when they are in a vacuum. Alright? Also, if we are going to put one proton and one electron on the other hand, they will still exhibit an electric field. Right? So here they will experience repulsion, okay, because they are equal in charge, and here they will experience a force of attraction because they are oppositely charged. Now, Coulomb's law would like to get the relationship between force over the magnitude of their charge and the distance. Now, they are at a certain distance with each other, or we can use R as a replacement for D in terms of resistance. In terms of distance. Alright, so Coulomb's law said that the amount of force that one experiences is equal to the constant value in a vacuum multiplied by the product of Q1 and Q2. So this is Q1 and Q2 over the square of their distance. Now we can say that since they are identical, so we can say that F is also equals to K Q square over R square, since they are identical. Now, the value of K here in a vacuum is 9 times 10 to the 9th power Newton meter square per Coulomb square. Right? That's the value of K. But where does the value of K comes from? It comes from the expanded form of K, which is 4 pi epsilon naught. Okay, what does epsilon means? Epsilon means the permittivity value. Permittivity value, which talks about the amount of resistance in the field. Okay, the amount of resistance in the field. Now let's talk about the amount of resistance in the field. Now there are two factors that affects the amount of force in the field, and that is what is in between the field, these two charges, right? Here, which is in the vacuum, here, what is in between these two charges is a vacuum. On the other hand, what is in between these two charges is a rubber. Since the material is different, then therefore the amount of force experienced by both charges in different environment will also be different. Now, the resistance made by this material are called dielectric. Right? A dielectric is any materials that are capable of resisting the electric field exerted by a charge. All right. So that means we expect that there is less resistance in a vacuum because it's a vacuum, and there's more resistance in the rubber. So the lesser the resistance, the greater is the force. That makes it force is stronger. On the other hand, the weaker or the stronger the resistance, the weaker is the force. So the force is weaker. So what is the value of epsilon naught? So the value of epsilon naught, by the way, epsilon naught is simply the permittivity in free space. Free space simply means vacuum, right? The value is 8.85 times 10 to the negative 12, all right, Coulomb square per Newton meter square. So if you're going to substitute it here in the expanded formula of K, that becomes K 1 over 4 pi times 8.85 times 10 to the negative 12. That should give you a value of 9 times 10 to the 9th power. So this proportionality constant is only true in a vacuum. But what about if the dielectric is a rubber? So if a dielectric is a rubber, then we cannot use this general formula over here because the K is different. So we expand the K, that becomes F equals to K, right? So we have K times Q1, Q2 over R square. And what is K? F. K becomes 1 over 4 pi permittivity of a rubber. Let's just use R and U. That means permittivity of a rubber multiplied by Q1, Q2 over R square. So our formula when it comes to problem involving a different dielectric, that becomes 1 in this case rubber. So that becomes Q square over 4 pi epsilon RU R square. So this is the formula for, and if the given value is present in the problem, such as the permittivity value of the rubber. Or we can also have it this way. Remember, we can find the ratio between the permittivity value of a rubber and that of the open space or free space, which is the vacuum. This is called the relative permittivity. Sometimes what is given in the problem is the relative permittivity and this one. So we only need to find the permittivity value of the rubber. So we multiply that cross, so we can get epsilon RU equals ER E naught. So we can rewrite this formula to Q square over 4 pi ER E naught R square. So there are two possible formulas that you can use when it comes to problems involving a dielectric aside from vacuum. When it's a vacuum, then you can simply use this formula over here. So an example is, okay, so example number 1. Example number 1, the given value are, we have it here. So F, since it is just a vacuum, so K, we can use Q square over R square. The value of K is 9 times 10 to the 9th power. Okay, what's the value of Q? Q here is negative 1.6 times 10 to the negative 19 Coulomb square over 1.0 times 10 to the negative 10 meter, of course, square. So having said that, you should be able to have a value of 2.3 times 10 to the negative 8 Newton. That's your final value. That's a force experienced by 2 electrons. Now what about the other one? So we have still, it's in a vacuum. So F equals to K Q square over R square. So 9 times 10 to the 9th power, that's the proportionality value. And 1.0 times 10 to the negative 9 Coulomb square. And 0.04 meter, because we have to convert that into meter. So you should be able to have an answer of 1.44 times 10 to the negative 5 Newton. That's the force experienced by 2-point charges. In this case, it's a repulsive force. So that's the end of our discussion, and thank you for listening.